Hello, everyone. My name is Tanisha Gupta, and I'm a sophomore here at OHS. I completed this project along with a group of students at Stanford AI for All summer camp. Our team split into two groups, which I will discuss later in the presentation. First, a little bit about our motivations for this project. Poverty is a major issue today. Nearly 35% of the world lives in poverty, and 11.8% of the US lives in poverty. Poverty has doubled in recent years. For many regions, while there are resources, it is difficult to identify where they need to be sent. Based on this information, our team came up with this problem statement. Determining impoverished locations using current methods is challenging, as current methods are survey and interview data. Many people in poverty do not receive the needed resources. Given satellite imagery, we want to use artificial intelligence to map low and high poverty areas. So, as I mentioned prior, the primary method of finding poverty levels is survey and interview data. One benefit of survey data is that it can help create data that is highly predictive and has high quality. Surveys provide a high level of general capability in representing a large population. There are three main limitations. It is expensive, hard to execute, and biased. In fact, phone surveys can cost anywhere from $5,000 to $15,000. Additionally, these surveys are very challenging and to actually execute, as they require a lot of manpower, time, and effort. Sampling bias often occurs because certain parts of the survey are underrepresented or overrepresented, and this inevitably leads to flawed data. Satellite imaging is a much better alternative. Satellite imaging is cheaper, and the average cost of raw satellite images is approximately $1 for each square kilometer. Satellite imaging also provides an advantage because it's more easily available and has far greater accuracy with no possible bias. There are two primary limitations of satellite image data, though. These limitations are that satellite image data is infrequently captured and that small objects are unrecognizable. So first, I'd like to give an overview and a description of the challenges we faced in our project. So the first step we took was collecting data, which in our case is satellite images of different regions in Uganda, visualizing results using a map that we created. We split into two groups. The first group worked on extracting features, which is key because it allows us to store less values, makes it easier for the model to find patterns, and is more data efficient. Our other group worked on the model itself by searching for the best hyperparameters. Hyperparameters directly affect the performance of the model, so it is key that we get them right. The image on the right shows us why hyperparameters are so important, because we can clearly see that one set of hyperparameters performed better than the rest. Throughout the entire process, we faced quite a few challenges. For example, our data was not linearly separable or able to be separated by a line. However, our model was a linear classifier, which attempted to find a linear separation boundary such as a line, plane, or hyperplane. Thus, it was hard for our model to perform well. For the feature extraction process, we had to make sure the features varied across the dataset. We also ran into the issue of not being able to pick the most obvious features. Income would have been the best feature because it directly tells you whether an area is in poverty or not. But we cannot identify that through an image. Lastly, while working on the model itself, we had to be able to determine the importance of accuracy, precision, recall, and figure out which one mattered the most. We also needed to interpret the graphs that we got back from our model and evaluate the hyperparameters based on that. Now, before we dive into our models, methods, and experiments, it is first important to understand what features are and how they are extracted. Features are parts of the image that are important to us and important to our task. In this example here, important features for the motorbike could be the wheels and the seat. Now, how are features extracted? There are different feature extraction algorithms. One of these methods uses convolutional neural networks, or CNNs. A CNN extraction involves pre-processing the image or normalization, which we will talk about on the next slide, image segmentation, and finally the extraction of key features and identification. As mentioned, feature extraction requires normalization. Normalization is the process of converting everything to the same scale. This is important because each of the features exists on different scales. If we don't normalize, we may weigh features differently in a way that we don't want. For example, we may weigh population much more than crop yields in this example because the population values are very large. With normalization, we can compare these two values on the same scale. Now I'll talk about the features that were used in our project. In order to determine the most optimal features to train our model with, we experimented with a set of pre-calculated feature extractions. There were 4 in total. Transfer features calculated by a specific learning algorithm called transfer learning. The ImageNet features calculated by CNN, pre-trained on the ImageNet dataset. The nightlight features extracted from the satellite images during the night. And lastly, our sort of ground truth, or the survey features extracted from the survey data. Next, we will talk about how we chose which features to use. This is an example of one of the functions we wrote and implemented to determine the best suited features for our task. In this feature search function, the model undergoes the training process for each of the pre-calculated features, which we store in a list as accessible paths to iterate through. We account for the bias term by concatenating an additional column matrix of ones to both the training and validation data sets. This function also determines the highest accuracy obtained by continuously updating the best accuracy value as it trains on each of the features. It then outputs it as well as the feature which enabled it for our further testing. But of course, we needed more than just accuracy to come to a conclusion. Therefore, we used various classification metrics to monitor and measure the performance of the model during training and testing. In particular, we evaluated the accuracy as well as precision, recall, and F1 scores, and with and without bias as a factor. The F1 score conveys the balance between the precision and the recall. Lastly, we integrated a k-fold cross-variation validation methods, especially useful when data available is limited. It enabled us to obtain an accurate estimate of the performance of the features on unseen data. This way, the classification metrics of each feature would be the most realistic, avoiding any risks of overfitting in the process. The simplified procedure is illustrated in the diagram and mimicked in our code. We split the shuffled dataset into K groups, and for each unique group, we took it as a test set and the remaining groups as a training set. We then fit and test the model using the various features on these sets and did this for each of the K iterations or slices. Most importantly, this method allowed us to retain the average overall evaluation score for each of our features and respective classification metrics. To come to a conclusion, we also determined the best mean and features as shown in this code. After revisiting the cross-validation techniques to our feature selection methods, we were able to obtain the following metric outputs for each of the 4 features with and without bias as a factor. However, we found that across each feature, the metrics were varying, making it hard to come to a definite conclusion. For example, the nightlight feature with bias had the highest accuracy of 73%, apart from the survey data. However, the same feature had very low precision and recall scores. This variance led us to conclude that the best feature didn't really exist overall. A reason behind this is that the features are nonlinear, as discussed in the challenges we faced. In order for the model to effectively utilize and learn from them, we needed one of higher sophistication, definitely a step to take in the future. So this is the methods and experiments from our model team. So implementing and tuning logistic regression was the main goal of the model group. Given n features extracted from satellite images, the goal of logistic regression is to find the linear separation boundary that best separates all the image points statistically, visualized on an n-dimensional grid in 2 classes, high poverty and low poverty. First, we input feature data as a matrix. Next, we apply a random set of weights to the data, which determine the importance of various features. Next, we calculate loss, which evaluates how well the line separates the data and updates weights with stochastic gradient descent / mini-batch gradient descent, which are algorithms allowing us to optimize our loss. Once the line is found, we use it to predict the possibility of an image indicating an impoverished or wealthy area, depending on which side of the boundary it lies. This method, while visualized best with only 2 features or 2D input data, generalizes to higher dimensions using mathematical formulas. We also implemented a support vector machine, which solves the same problem as logistic regression, although through a geometrical rather than statistical approach. Now we'll discuss methods we use to optimize the model's performance. Hyperparameters are parameters of the model, or variables that determine the structure of the model. It is crucial to tune these values to enable your model to learn properly, as they have a large impact on the performance. We observed differences as high as 60% in accuracy after changing a few hyperparameters. Cross-validation. Like the feature team, we used tenfold cross-validation, just reapplied to the problem of determining hyperparameters that enabled generalization. We employed a 90% to 10% train test split, dividing our data into tenfold. We then ran the model 10 times, each time using a different fold for testing data, and then averaging the performance at the end. This allowed us to evaluate our model on the entire data set, not just a single train test split with possibly skewed data. And now for our hyperparameters. There were 4 in total. Learning rate, a control of how much the model changes in response to the estimated error when updating its weights. The epochs, the number of passes of the entire training data set the machine learning algorithm has completed. Batch size, the number of training examples utilized in one iteration. And lastly, regularization rate, a hyperparameter which blocks the formation of more complex models and helps us avoid overfitting. This is the hyperparameter function that we wrote and implemented. It outputs the best accuracy and which feature had it for further testing. We ran this experiment several times in order to find which parameters were giving us worse accuracy and eliminated them. We also expanded the search to account for precision and recall as well. We also experimented with a SVM in order to see if that would give us a better accuracy. We used the features that were given to us by the features team and the models team for this model. The purpose of trying the SVM was to check if perhaps it would work better than our logistic regression classifier for not just accuracy, but also precision and recall. We tried out using the logistic regression model from sklearn and a k-nearest neighbors model. So results for the model section. So for our final results, the best model was the logistic regression model, the one we made ourselves. You can see the final loss curve here, and our final loss was 0.76. The best accuracy we achieved with all of the tuned hyperparameters and features was 65%. The best precision was 30%, and the best recall was 70%. The best hyperparameters were a learning rate of 0.01, a regularization rate of 0.1, a batch size of 32, and 100 epochs. Through our testing, we noticed that really small batch sizes and really high learning rates were not the best, and that moderate values for both of those were the best. And while using sklearn models for logistic regression and SVM, we also discovered that we could improve our results by specifying the class weight as balanced. This simply adds weight to our ones class since it's less frequently present in our input data, allowing us to achieve an even better performance of around 75% accuracy. So this is our final logistic regression prediction against the actual labels. The red dots are areas of high poverty, and the low dots are the black dots are areas of low poverty. Poverty is a really big problem. This is a conclusion and next steps. So poverty is an extremely big issue that needs to be solved, with close to 35% of the world's population living with under $2 every single day. Past efforts have included surveys where members go out into all parts of the world to determine poverty-stricken zones. However, this is too time-consuming. AI can efficiently be used to map global poverty regions through classification models. So, as a recap, we have 4 different sets of features: transfer, survey, nightlight, and ImageNet. Our goal was to figure out which set of features allowed our model to perform the best. We initially set out by measuring the accuracy of each feature, but we soon realized that we needed more than one metric to accurately evaluate the features. So then we calculated precision, recall, and F1 scores. Lastly, we used cross-validation to get an accurate sense of each metric and prevent overfitting. With all of these methods, we found that the best results actually depend on the metric you were looking at. If we look at the images on the right, we can clearly see that for accuracy, the survey performed the best. But if we look at the F1 score right below, we can see that ImageNet actually did the best. So it all depends. For the model team, we used to define the best hyperparameters for the data sets. It defines the structure of the model and significantly affects the accuracy rates that the machine predicts. We used k-fold cross-validation with the 9-10 training testing split. Classification models were logistic regression and SVM, which were both utilized to classify the data into low poverty and high poverty regions. Support vector machines work by maximizing the difference or margin between the hyperplane and the nearest points. Feature testing, different features were utilized, including transfer features, ImageNet features, nightlight features, and survey features. So for our final conclusions, neither logistic regression or SVM worked very well. And through visualizations of our features, we realized that the data was not even remotely linearly separable. Instead, data points in different classes were tangled up together. So collectively, our feature extraction and model team determined that the most important next step to take is to implement a convolutional neural network, which can use nonlinear separation boundaries to more accurately classify the data. Thank you all so much for your time and for listening to my presentation. Thank you.